We're here to talk about blood glucose regulation. Now you know what it's like when you get low on blood sugar, right? You get tired, a little fuzzy-headed, things like that, maybe a little hangry. So it's really important, especially for our brain, that we maintain a steady level of blood glucose. Cells are marvelous little things, but they can't do everything by themselves. Especially not if they've signed up to be part of a team, right? The 30 trillion cells that make up a multicellular organism like us. Each cell kind of gives up some of its rights and says, well, I can't do everything myself. I'm going to leave it to some other cells to do some of this other work. And so our body requires a lot of coordination. We need to look outside the cell to figure out how that's done. That's true for blood glucose and a variety of other things. But let's start here. The idea of homeostasis is really never far from our minds when we're studying the human body, or any life for that matter. It's just so necessary to keep things steady. It's how we keep our body operating normally, but this isn't for free. It's something we really have to work at. And our body does this on a larger scale through these negative feedback loops. And that sounds like a bad thing, right? When you get negative feedback, somebody tells you, you did a terrible job. That's no fun. But it is corrective. And in that sense, it's a good thing. And that's what we're trying to do to keep homeostasis. One part of the body has to monitor blood glucose going down and say, hey, get that blood glucose back up. And then changes take place to bring it back up. If the blood glucose gets too high, same thing. Hey, get it under control. And then the blood glucose starts coming back to a normal level. So in that sense, a negative feedback is really a good thing. We need those corrective mechanisms to make things work. Now, of course, we're scientists, so we have to graph things. Let's take a look at what that would be like on a graph. So if we were to look at blood glucose over time, then homeostasis would mean that it'd be pretty steady, right? Yeah. And there's what we might call a normal physiological range, sort of a range where it's acceptable. Maybe it's a little high, but it's fine. A little low, but it's fine. And sort of our target right here, we would call our set point. Kind of where our body's programmed to that says, I like it best right there. So for blood sugar, it's around 90 milligrams of glucose for every deciliter of blood. We can tolerate up to 120, and that's okay. Maybe that would be after a meal. We can get down into the maybe 70s, and that's okay. Beyond that, you really start feeling the effects. And you might start wondering, I wonder if I need to go to the hospital. If we get above this, we're indicating maybe diabetes. Below this, hypoglycemia. So we want to keep things in an acceptable range, and that's the job of the negative feedback loop. Like I said, if blood sugar starts to climb, then other parts of our body take over and say, hey, get that under control, bring it back down. That's the negative part, right? It goes back in the opposite direction that it started. So if it went positive, it goes negative. And same is true if it starts to go down, then the body needs to bring it back up. For the most part, it should stay in this range. And if that's the case, the body's pretty happy. Well, let's take another look at the negative feedback loop, just so a model with something that's familiar. Our heating and cooling system in the house. Basically, a few things need to happen to keep homeostasis of room temperature. So we need to monitor that. There's some sort of thermometer somewhere. Then you got your thermostat, which you program to the temperature you want it, and then you have your heater. Obviously the opposite in the summer when it gets hot, and you got your AC unit. So there we go. All three of these things need to work, and they need to be in a loop as well. So this has an effect. It blows hot air out. But we don't want to say, hey, it's too cold. Turn this heater on and then just leave it on forever. We need to get this feedback over here where the temperature is sensed constantly and telling the thermostat, hey, this is what we should do. So here's kind of a formal way of looking at this, and we can apply this to the body as well. So first we need a sensor. Sensor's job is exactly what it sounds like. It just monitors things. It's not very smart, it's not very sophisticated. It just says it's 68 degrees, it's 68 degrees, it's 68 degrees all day, every day, 24/7. So this is currently sensing 68. That doesn't do any good if it's just all on its own. It needs to have some way of signaling the thermostat. It's probably in here somewhere. We have this that we've programmed in, the temperature that we want. That's our set point. So we got our set point. This then needs to give it some thought, right? It needs to say, that's 68 degrees, I'm set to 70, what do I do now? So it's got this little computer circuitry in here that figures that out. The old ones had this mechanical switch, but there's some way of integrating this information. And so we call this sort of computer the integrating center. It could also be known as the integrator or even control center, but it's just integrating information. And this is our decider, right? It's the decision maker that says, that's too low, I need to be at this, but neither of these things can change anything about the room temperature. So this sends off an electrical signal to our heater over here and says, hey, light the fire, blow that air out, get it warmer in the room. And so this thing here is the muscle, right? It's the thing that actually does something about room temperature. So that's the effector. The effectors are the organs in our body that do something, that create that change. And they're never really the same as these sensors or integrating centers, although sometimes these are combined. Like they are in your house, that thermostat has a thermometer within it. Well, there we go. But this is still a bit incomplete. This is going to produce heat, and that's going to raise the temperature. And so that heat feeds back to the sensor, which is just sensing temperature at this point. And if that changes, it's getting warmer, 69, but now it sends that signal, it says 69, and it says, nope, not enough. Keep heating, gets a little warmer, gets to 70, and now tells the thermostat, and the thermostat says, hey, that's perfect, let's turn the heater off, and we're done. Now we're at homeostasis. Yeah, but couldn't you just like put on a jacket or do push-ups or something to get warm? Yeah, you know, that's a good point. You could just run around or do push-ups or put on a jacket. And I think that's an important point. This is just an automatic system that's going that we don't have to think about, really. But there are other ways we can warm up our house. We can light a fire in the fireplace, but that's not as automatic. So in our body, there are systems that are automatic to keep our body temperature normal. But then there are those other systems that, you know, we can just use our brain for. We could just put on a jacket. We could run around or do push-ups or things like that. So we don't only rely on these automatic systems. Same goes for blood glucose. If our blood glucose starts dropping, this automatic system will take care of it, but we can also eat an apple and that'll raise our blood sugar. So there's more than one solution, but this is kind of the automatic background stuff. Let's take a look at blood glucose. All right, so here we go. I like to think about what's actually happening in the body rather than just dissect all this so much. There's an advantage to putting things in a format like this to help us understand and really break it down and analyze what's going on. But I don't think that should separate us from the human body. So let's take a look at both here. So when we're regulating blood glucose, let's take a look at it and say, what if blood glucose, this factor that I'm regulating, starts to increase? I tend to start here. In the end, I want to have some effect that's going to bring that down, right? That negative feedback. It's too high, get it under control. All right, I'm going to bring it back down. And so what in your body senses this? Just drawing a few organs. We got the heart and the blood vessels, the liver and the pancreas. and it's the pancreas that does the sensing. Now the pancreas is a complex organ, it's hidden right there kind of behind the stomach. Looks almost feather-like because of all these ducts. It makes lots of our digestive enzymes, but they're these little, they're called pancreatic islets, these little clusters of cells that sense blood sugar. There's two types of cells. There are alpha cells and beta cells. But I'm just going to use the term pancreas. We can be more technical and say that high blood glucose is sensed by the beta cells. But let's just put the sensor as pancreas. All right, so the pancreas is the sensor. And now we need an integrating center, something to say, hey, is that okay? Is that too high? Is that too low? And we need a set point. Our set point, we said before, was 90 milligrams per deciliter of blood. So the deciliter is kind of a strange unit of measure. You don't see it very often other than in the medical setting in units of measure for blood in particular. And so you probably are familiar with a milliliter, really small amount of fluid, just several drops. And then a liter, a deciliter is 100 milliliters, so about up to there on the liter bottle. All right, just a bit of an aside, a little sciencey thing. Okay, so that's our set point. Who's programmed with that set point? It's actually the pancreas again. And this is where this kind of formalized system gets in the way, in my opinion, to a certain extent. It's a bit confusing. The pancreas to the pancreas is the same cell, it's just doing two jobs. So I think this is a bit of a stylistic thing, or however your professor wants it done. I tend to put these in the same box, and just, if I had to label it, I'd say they're both sensor and integrating center. Or we could just put it this way and be super formal and analytical about it. All right, well, the pancreas itself can't do a whole lot about the blood sugar, but it does release hormones. And so there wasn't really a pathway from this one to this one. They were the same cells. But from the pancreas to the effectors, the parts of your body that can actually change blood sugar, there has to be a path. And this path right here is insulin. I think I should have planned out my boxes better. Anyway, now we're going to hit an effector, something that changes the blood sugar. So the insulin, if we look over here, gets released by the pancreas, goes into the bloodstream, goes into the heart, and goes all throughout the body. So every cell in your body is exposed to insulin. The liver is one of those organs that responds to it. It's right there under your rib cage on your right side, really big organ, and it's a good sugar storing organ, and that's what it's going to do. So the liver is one of our main effectors. And I also like to add in my diagrams, I just don't have room here, what happens. So the problem was we had too much blood glucose, and so we want to take it down. What the liver does is it brings in glucose and converts it to glycogen. So that would be dehydration synthesis, just putting together all those bits of glucose into a big molecule that can be stored and won't go anywhere. We can use it later, and will if our blood sugar starts to drop. All right, so there's the liver. We've got a decrease in blood sugar, and our sensor should then pick that up. The pancreas knows, hey, blood sugar is back down, we're normal, stop releasing insulin, and things just kind of go back to a steady state. So liver releases glucose into the bloodstream, goes around, pancreas senses that, stops secreting insulin, back to normal. One more nuance on this. The liver is not the only effector. So sometimes there's multiple effectors, more than one organ working here. So I'm going to branch my diagram like this and add another box for the body cells. Now that's kind of a vague effector, isn't it? Well, we did say that insulin went all throughout the body, so there's just a cell in the body. All right, so all these bodies, red blood cells, everything else, respond to insulin. What they do is they add a little channel for glucose to come into the cell. May not seem like much, but you multiply that effect times 30 trillion cells, and that's a lot of glucose out of the bloodstream and into cells. They're going to use it up, chop it into bits, make ATP with the energy, and you're off and running. So body cells, they take in glucose, which also decreases it. And now our loop is complete. So that's kind of the formal presentation of a negative feedback loop for blood glucose, specifically in response to blood glucose getting too high. What I'd like you to try is what would happen if blood glucose dropped. Same setup, so set it up for yourself the same way. Draw it out. I'll give you a hint. You're going to start with the pancreas. These are actually the alpha cells, but you're going to release a different hormone, and you're going to have a bit of a difference in effectors. It's actually a little bit simpler. So I'm going to leave that one for you to try on your own. Last thing I wanted to bring up is if there's negative feedback loops, is there such a thing as positive feedback loops? Probably wouldn't have brought it up if that weren't the case. There are. They operate in the opposite direction. They're not real common. So we said with a negative feedback loop that if some factor like blood glucose or blood calcium or blood sodium were going up, then that system was meant to bring it back down. But a positive feedback loop, instead of giving them negative feedback, hey, get that back in line, they're giving them positive feedback, saying, yeah, keep going, keep doing more of that. Now that's not going to be homeostasis, right? If we were to graph that out, then something would start to increase and the body would say, keep going, and it would keep increasing. So that's not homeostasis at all. An example of this would be childbirth. So you start with no contractions, get to be some contractions, which causes pressure on the cervix, and the body says, yeah, that's a good thing. And so steadily that pressure increases and increases and increases until the baby's born, and then the system just stops. It's kind of the single use type of thing. It's usually for purging something from the body. So a very different purpose, but a necessary one in that case. If you had a negative feedback loop for childbirth, there'd be some pressure and your body says, oh, we don't like that, which is probably true. But then the baby would never get born because the contractions would start and then the body would stop them. So there's that one. Vomiting is another one. You get a little nauseated and then it gets more and more queasy until everything comes out. There's a positive feedback loop. Not homeostasis, but it does have its own purpose in regulating the human body. Well, there's blood glucose regulation. Kind of a nice thing that we don't have to think about this in order for it to work. And this is a particularly important one because our brain runs just on glucose, and so we need to keep those levels relatively high so that our brain keeps working. There's several mechanisms for regulating that, many of them hormonal, but there's also just behavioral mechanisms. We get hungry, we eat. And so don't get stuck into thinking that these negative feedback loops are the only way this happens. This negative feedback loop is a common mechanism that you're going to see more and more. We'll practice a little more in this class talking about body temperature regulation as well. And this is all kind of a warm-up for getting to anatomy and physiology. When you start talking about the endocrine system and the nervous system, you'll run into more of these and learn how the body regulates other factors like calcium, potassium, sodium, and the list goes on. But it's an important mechanism to understand the basics of and kind of gives us a chance to look outside the cell. That's it for this time. Until next time, remember, life is good, especially if you're not hangry.